All right, so this assignment has us draw an isomorphous phase diagram, and that's that banana-shaped diagram where both materials were completely soluble. So the minute you see the word phase diagram, you are drawing a map of what phases are present as a function of temperature. That's always the axis, the vertical axis. On the horizontal axis, you have your two elements, and it's not going to matter which one you put where. But let's just call that the silicon side and this the germanium side. So by writing germanium over here on the right-hand side, what I mean is over there, we're talking about 100% germanium. And what that means is that over here on this side, there's 0% germanium. Likewise, where there's 0% germanium, there's 100% silicon and 0 silicon. So always kind of keep in mind that while one thing is dropping, the other one is rising. For shorthand, what you're going to find is that I am very frequently just writing silicon on the left-hand side and germanium on the right-hand side. And what I need to go on in your head is for you to realize that with germanium on that right-hand side, it's going from 0 all the way on up to 100% germanium. So just keep that straight in your heads. Okay, so we have been told the melting point for germanium. All right, so that germanium is melting at 940 and silicon's melting at 1412. So that means that over here, we've got a melting point of 940. And then over here at a higher temperature, we have a melting point of 1412. So that's it. We have begun this phase diagram. And I kind of know where this problem's going, so I'm only going to draw part of the banana-shaped curve. I'm only going to draw the lower part. That would be the solidus. I'm going to hold off on writing the liquidus for a minute. I'm gonna actually dash one in so you can kind of see. It's going to be something like that, but where precisely it is going to depend upon what we're going to answer in B. So this upper curve is what's called the liquidus. It separates liquid, which is up here, from solid. So the name of that curve is solidus, and the name of this region down here is solid. In between, we have liquid plus solid, and I'm going to draw that in just blue so you can see what I mean. So this inside the banana, we have liquid plus solid. Okay, so let's move on to B. We've taken care of A. In B, it's telling us to create the location of these curves, this liquidus and solidus, in such a way that at a particular state point, we've got 25% liquid. So I'm going to circle the thing to pay attention to right here, which is this 30% germanium thing. So at 30% germanium, which might be right about here on the phase diagram, we're going to draw a vertical line going all the way on up. And at 1250 C, and we can't tell exactly where that is, but let's imagine that something like, I don't know, something like this temperature is 1250 C. So that's the state point right there. At that state point, we need to draw the shapes of these banana pieces such that we end up with 25% liquid. So this is the hard part of the problem. So we need to apply our understanding of the lever rule to make there only be 25% liquid. So let me just kind of switch colors. I'm going to switch to a shocking green here. So the portion that is not touching the liquidus, so that portion of the curve, relative to the total portion, so let's make that red, relative to the total portion, the line length segment that's going to go, I'm trying to think of how to draw this best. Let's make this purple. So that green portion relative to this that ratio needs to be 25%. So right now that's looking to me at, actually it's not looking bad. Let me just kind of draw this a little bit better. I actually did a pretty good guess here. So what I am saying is that little green length divided by this total line length should be 25%, and that actually looks pretty close to 25%. So I'm going to finalize the liquidus curve by drawing that in such a way that we end up with a ratio that kind of makes sense. So I'm going to clean this up a little bit. I'm going to erase this part right here. Okay, and I'm going to draw my 1250 back in. So at 1250, gosh, it erased too much. So at my state point, which was that, and at 1250, I want the ratio of this to the total line segment length to be 25%, and I think I've pulled it off. Okay, so 25% is the ratio of that little shaped curve there divided by the total line segment length there. And so that is now an acceptable solution for B. All right, moving on to C now, I'm gonna actually kind of just switch to a dark green color. So I'm now answering C in dark green. In C, this is easy to answer. All you have to do to answer what is the composition of solid is you're gonna, at your state point, read over. Oops, I went to the liquid side. Actually, we're going to read over to the solidus, and then we're going to read down. So the composition of the solid for this phase diagram looks like to me, oh, I don't know, if that was 30, I'd say that's about 15. So our answer to the composition of solid is 15%. 15% germanium is the composition of solid. So what's the composition of liquid? This time we're going to read over to the liquidus and down. That looks to me, I don't know, let's call that 70% germanium. So the composition of liquid is 70% germanium. Finally, in D, we're supposed to sketch what a sample of this material at that composition looks like. Now, we were told it was 25% liquid, right? And we set it up to be 25% liquid. So I'm going to kind of scroll down so I have a little bit of room to draw. What we're simply going to draw is, you draw these things in a circle to signify that's what you're looking at in a binocular, microscope. And then I'm going to draw 75% of this stuff as being solid. So 75% of it is solid, 25% is liquid. So I'm going to draw some large blotchy things with grain boundaries that represents my solid, and I'm trying to cover up about 75% of the field of view. So I think I've done it. That looks like about 75% of the field of view. So that's solid. Sorry, that's supposed to say solid. And I'm going to put in parentheses 75%. And then the remaining stuff in here, right there, that would be liquid. So that's what a sketch of the microstructure would look like. We've got some solid material with grain boundaries, and then the rest of it is just sort of floating in this liquid. All right, so that's it. That's